Professor Chris Reynolds is the has broad interest in observational and theoretical high-energy astrophysics. Much of his work and that by his group centers on the astrophysics of black holes and the role that they play in the universe, addressing 4 specific themes: observational problems of relativistic physics close to the black holes as probe of physics beyond the standard model, and theoretical studies of accretion disk, and theoretical studies of the influence that supermassive black hole have on galactic scale structure formation. And Professor Chris Reynolds is the principal investigator of the Advanced X-ray Imaging Satellite Axis, and he is now the Plowman Professor of Astronomy at the University of Cambridge, and also the College Park Professor at the University of Maryland here in the US. So the floor is yours.
Thank you, and many thanks for the invitation to come and speak to you about Axis. And so I'm very excited on behalf of the whole team to be here to tell you about this project. So let me just. Okay, this is our slides. This is how I'll be structuring the talk today. Any discussion of X-ray imaging must start with a discussion of Chandra. So I'm going to sort of help set the scene by giving a very quick run through Chandra's legacy to astronomy and astrophysics, and then discuss by way of introduction to Axis, discuss the programmatic landscape that has led to the current Axis concept, the Advanced X-ray Imaging Satellite concept. I'll then probably spend maybe the bulk of my time talking about the science of Axis, some of the exciting investigations we believe we can achieve with this future observatory, and then a little bit at the end about how we actually go about constructing and building the observatory, and then the timeline there. The sort of in terms of bookkeeping, just one quick. I can't see hands that are raised when I'm presenting, so please feel free to just cut in if you have questions, or of course I'm happy to also take questions at the end. So it was more than 23 years ago now that Chandra was launched. This is a month after I got married, so I remember it quite well. We just had a 23rd wedding anniversary. So. And since that point, Chandra has really defined a whole new epoch of not just X-ray astronomy, but of astronomy in general. And the key enabling technology to this was the exquisite imaging that was enabled by the high-resolution mirror assembly of Chandra, permitting the half-arc second imaging capabilities of Chandra. Now, of course, Chandra is a highly capable multi-instrument observatory. Also has extremely capable spectrometers, grating spectrometers on it, and indeed, much of my own science with Chandra has actually been more on the grating spectroscopy side than per se the imaging side. But in terms of sort of setting the scene for Axis, I want to just quickly run through the legacy of Chandra in the imaging side of things. And so, starting close to home, it really has, Chandra's had impact across the full gamut of the universe. So, in our quick dash through the universe, let's just start with planets. You don't normally think of planets as a realm of high-energy astrophysics, but of course, Chandra has allowed us to study the interaction of the solar wind with planets. And this object needs no introduction. With Jupiter, we can see the auroral emission, and this is Mars, where you can see the Mars with Chandra. And what we're seeing here are processes by which the solar wind is interacting with the tenuous atmosphere of Mars, producing charge exchange and fluorescent emissions. So we can we can study the impact of the solar wind on these planets with X-ray observations. Now, moving slightly further out, Chandra's has left its legacy on our understanding of stars, and in particular, across the gamut. But for stellar birth, it's allowed us to probe dense regions of star formation. This is Chandra image of the Eagle Nebula, where a large number of these sources you see here are young stars that are formed in the nebula. There's even one or two. I mean, some of the stars are embedded in these famous pillars of creation from Hubble are foreground, but in fact some of the bluest objects here are probably deeply embedded protostars within the nebula. And these data have been essential for allowing us to probe magnetic activity, and as young stars are created and then gradually lose their protostellar disks. And then over here we have the beautiful comparison of Chandra, which is the purple here, with the recent web data for the Carina Nebula. On the other end of the stellar life cycle is stellar death, and here I just highlight Chandra's impact on understanding of supernova remnants. And a very, very famous image from very early on in the mission was the Cassiopeia A supernova remnant, which when combined, the exquisite imaging when combined with the CCD resolution spectroscopy enabled by the ASIS detector on Chandra, has allowed us to really map out the elemental abundances of these supernova remnants. So this is color coded by element, and I real time I couldn't run through exactly which colors are which elements, but this is color coded by the element of the emission, and you can literally see the star sort of turning itself inside out with these kind of data. And with Tycho, this is actually pulled from Belinda Wilkes' recent review article on the impact of Chandra. And one of the things which, with my hat on as someone interested in plasma physics, I think is quite wonderful, is you start to see these stripes or these modes, these waves being set up in the high energy emission of the Tycho supernova remnant that are thought to be due to a current-driven instability associated with the cosmic rays that are produced in this supernova. So this is sort of a direct evidence of the classical notion that supernova and supernova remnants are important sources for cosmic rays. In this quick dash through the universe, sort of moving a bit further afield to the galactic center, Chandra's had huge impact on our understanding of the crowded center of our galaxy, and in particular, Sagittarius star at the supermassive black hole at the center of our galaxy, the 4 million solar mass supermassive black hole. And it's allowed us to map out the gas that is actually likely, the gas that's accreting onto that black hole, and therefore sort of sets crucial boundary conditions for understanding, for example, Event Horizon Telescope images of that supermassive black hole. Leaving our galaxy, this is getting very much into my own science here. I think it is true to say that Chandra has had an absolutely profound impact on our understanding of the interaction of black holes with structure formation. Indeed, I would make a case that the whole field of AGN feedback really started with X-ray observations of galaxy clusters and elliptical galaxies by Chandra, and then shortly after by XMM. So the fact that black hole accretion and the active galactic nuclei that are associated with that can actually pump energy out into regions of space that are tens of kiloparsecs or more, and therefore create a feedback loop that stops further star formation from galaxy building from happening. Really quite an extraordinary and profound discovery by Chandra. And then finally, in this dash through the universe, going out to very high, to the largest possible scales, Chandra's left a deep legacy in understanding of AGN evolution through its deep fields. So this is the Chandra 7 megasecond deep field. There's, I believe, roughly about 800 sources here. And these are some of the faintest X-ray sources known. And this allows us to build a quantitative picture of AGN evolution back to, of order redshift 6, depends upon exactly what luminosity cutoff you put there, but you can understand AGN evolution with these data back to a very high redshift. So that's the legacy that Chandra has left us, and Chandra is still operating and doing fabulous work. But we want to make the next big step beyond that, big step in terms of especially collecting area, but then also, as we'll see, there's certain other dimensions where we wish to make a big step beyond Chandra. So this is the motivation for the AXIS concept, the Advanced X-ray Imaging Satellite, that a group of us have been thinking about for some time now. So this was the report we put together before the Decadal Survey for consideration by the Decadal Survey, and the archive number is up here if you're interested in seeing it. And Richmond Shotsky was PI of AXIS at this time and up to actually earlier this year. And this is the team, the first team meeting we have. So Richard is hiding back there, but of course really should have been front and center. And then this is the team of the first core team of AXIS. Now, before really diving in and telling you about exactly what AXIS is and what AXIS will do, let me just sort of set the programmatic background for this, because I think this will help you understand exactly how we're phrasing AXIS. So, of course, the Decadal Survey, the US Decadal Survey, reported last November, and this very much, of course, is driving the NASA's future investment. So the Decadal Survey organized their discussion of astronomy and astrophysics into these three big science priority areas, which one way or the other sort of encapsulate most of what we all do. So there's cosmic ecosystems, which is essentially everything associated with galaxies and galaxy growth and feedback processes. You've got new messengers and new physics, so cosmology and multi-messenger astronomy, and then the suns and worlds in context. So of course, stellar physics, exoplanets is all in these first. So these are the three big priority areas, and the Decadal Survey recognized that X-ray astronomy is essential for every one of these priority areas. Now, many of us, I suspect, I can't see exactly who's in the room there, but I suspect many people in the room there, and certainly myself and others online, were very invested in putting forward the next big US flagship mission for consideration by the Decadal Survey. So this is LINX, and the LINX concept is a highly effective observatory for take the next giant step in X-ray astronomy, and in particular, it's got three distinct instrument packages on it. So the high resolution X-ray imager, the microcalorimeter for very high resolution non-dispersive spectroscopy, and then the grating spectrometers for extremely high resolution soft X-ray spectroscopy. And I think we look forward to the day that LINX will fly. It was disappointing, I think, to many of us that LINX was not ranked #1 by the Decadal Survey. Instead, the flagship that was ranked for the Decadal Survey was the large IR optical UV flagship, so the so-called Louvois X, which, as you can see in the Decadal Survey's timeline, is slated for a 2045 launch. So with a recognition that, of course, this, if you don't do something, this brings tremendous imbalance to the field, the Decadal Survey explicitly recommended that there be a new line of missions brought in, the so-called X-ray probes, the so-called probe class missions, and that in recognition that the next flagship they were recommending was the IR optical UV flagship, that the next probe, the probe that would fly at the end of this decade, should be either a far infrared mission or an X-ray mission designed to complement Athena. And that sort of sets the initial that's the starting gun for the probe, X-ray probe concepts, and in particular axis. Now I've highlighted in red the design to complement Athena. I think as a programmatic issue, for programmatic issues, that requirement's actually formally been dropped from the probe call because of some of the redefinition processes that are going on for Athena right now. But still, I think it's an important consideration to think that, you know, if and when Athena flies, we should be complementary to it. Okay, so that's the boundary missions from the decadal survey. NASA moved to implement that relatively quickly, quite aggressively. So in January, they put out a community announcement creating the probe program, and then the draft announcement opportunity came out just this summer. And the price cap here, so for these missions, is $1 billion. So this puts us in the point where we're significantly larger than the standard Explorer program, say significantly larger than Mid-X, but of course well below that of a flagship mission. So, but also with quite an aggressive timeline, as we'll see. Okay, so without further ado, let's jump into discussing what AXIS really is. So AXIS in a nutshell. So our concept is we will be a observatory focused on high resolution X-ray imaging. We'll have a point spread function of 1 arcseconds on axis, so you know a little worse than Chandra on axis, but because of our mirror design, we can maintain a very good point spread function to quite far off axis, off the optical axis, so we can degrade to only about 1.5 or maybe 1.6 when we're 15 degrees off the axis. So this gives us sort of a very flat ability to image. Our baseline collecting area, effective area with you know all the including all the filters and quantum efficiencies will be 5,700 square centimeters at 1 kV, and maintaining significant effective area out to 6 kV and beyond. So we even have a little bit of area out to 10 and 12. And then a relatively large field of view, so 24 arc minutes by 24 arc minute field of view. Here's a bandpass. Now, of course, to support this, we need fast readout detectors so that we don't completely saturate on even faint sources. So as I'll discuss a little bit later, we have CCD readouts with greater than 5 frames per second to support the effective area and the resolution. And then the other capability that we want to be responsive to is a transient follow-up. So we have a fast slew rate at 120 degrees in 5 minute slew rate. And the final thing here, just to highlight, is our orbit. We're going to be in low inclination orbit, low inclination, low Earth orbit. One of the surprises becoming PI of this mission, and you know, Richard was telling me this well before, but you know, $1 billion goes away very, very quickly. It's not much money when you start to actually look at this. So you know, we're a very simple design, and that's sort of key, I think, to the robustness of the concept. We're a simple single instrument design. So an X-ray optic, and then a single detector technology at the focal plane with a sort of fixed optical bench. And I'll discuss a little bit later about the mirrors and the detector. Baselining a 5-year prime mission, and that's dictated by the announcement opportunity. But we want to design for you know, another 5-year extended mission beyond that at least. So make sure there's no design aspects that preclude a 10-year total mission lifetime. And then the other thing which is very important for both our concept and is also mandated by the announcement of opportunity is that this is a true community facility. The idea is, it's mandated that greater than 70% of the time of the observing time be allocated to guest observers. So less than 30% must be science team time, that is completely consistent with the notion of the axis having an extremely broad reach, an extremely broad and versatile science program that can be done with it. And I say the other strand to this will be an active TOO program and transient follow-up program. This is just, so again, highlighting the orbits we're going into. So this is one of the big differences to Chandra is going into a low Earth orbit, and I can discuss the motivations for this if later if you're interested. But the principal one being the desire for the lowest possible instrumental background, so we can see the faintest sources and faint diffuse sources, and then also the communications associated with fast transient response. It's very beneficial to be in low Earth orbit for that. Okay, so let me just now jump into the science of Axis and spend probably a chunk of my time talking about this. So I will be phrasing this, but in terms of answering decadal survey questions. That's very much the charge we've been given from putting these probe class missions together is directly to address decadal survey priorities. So that's how I'll be phrasing this. So one of the top decadal survey priorities is the question of the origin and growth of supermassive black holes. So this is actually quoted from them. What seeds supermassive black holes and how do they grow? Indeed, this was a question that was posed separately by two of the science panels. So it's really a very high priority question for the decadal survey science. Now, for those who are not enmeshed in this field, what's the big question here? Well, as much as we talk about supermassive black holes, we still really don't have a good idea of what their origin is. Are they at sufficiently early times in the universe? What seeded those black holes? Were they seeded by the remnants of the first stars? So say 100 solar mass seeds, which then rapidly grew. Or are they seeded by the direct collapse, sort of monolithic collapse of galactic cores, so directly collapsing to say 10 to the 5 solar mass black holes? And it's been a sort of holy grail of AGN studies to try to push back to a high enough redshift and to low enough black hole masses that we can really start to assess this question. So I like to think of it as here we have time going from top to bottom and mass going from left to right. The supermassive black holes we know and love today are over here on the bottom right of this plot, but we don't know what the different on-ramps are that nature has taken to give us those supermassive black holes. Now, this was a prime focus for LINX, because LINX can directly see those early black holes. You can actually see them basically as soon as they're forming. But with Axis, we can actually still push back to the point where we are sensitive to which of these on-ramps you've taken. So that's a big focus. Now, distinguishing the models requires census of what I call baby AGN, so low luminosity AGN, beyond the redshift of 6, and so the Axis survey strategy is designed to find that. So we have a survey strategy of wide, intermediate, and deep fields, and in our deepest field, I've listed a few numbers here of the projections of what we'll find. We'll find 3,000 AGN, and some number of those will be beyond the redshift of 6. will be, but at this point, more galaxies than our AGN, and we'll find a few clusters and protoclusters as well. So this compares these numbers with Chandra here. So really, it's our collecting area, and it's our collecting area, and the flatness of our point spread function is letting us drive very deep. So this sort of gives you a visual impression of what our axis deep field will look like. So this is our full field of view, and this is compared to the current state of the art with Chandra. And to sort of highlight the point that while we won't be detecting the first black holes, just to highlight that we are still sensitive to the seeding mechanisms. I'd like to sort of show this, which is courtesy of Fabio. And this sort of shows calculations of different scenarios, sort of a light seed scenario, and the mixture of growth of black holes by accretion versus mergers. And it shows that as you go to high enough, when you go to high enough redshift, you start to pick up this population here of low black holes, which is merging principally which is growing principally by mergers, as compared to a massive seed scenario where you pick up a population that's growing, principally by accretion, and by taking sensors, by taking luminosity functions of black holes in this region, we can tell which of these scenarios we're in. Let me skip over this to address another question, or the second half of the same question with decadal survey, is how do these black holes actually grow? And so coming to lower redshift, what another important goal of AXIS will be to survey both growth by mergers, by supermassive black hole mergers, and by obscured accretion. And with the mergers, our surveys will reveal large numbers of dual AGN. So this plot over here is actually, or this figure here is another one of the classic Chandra results of the dual AGN in the nearby galaxy NGC 6240. And if you wind the clock forward a few tens of mega years, maybe these black holes will merge and will be a LISA source. So with AXIS, we'll be able to get population level statistics as a function of redshift on these kind of systems, and will let us really test both the merger and the accretion driven scenario for growth. To get to the next topic is the basically AGN feedback. So decadal survey asks, how is the growth of black holes coupled to the evolution of host galaxies? And as I highlighted earlier, I think this is an area where X-ray astronomy and Chandra in particular has had an absolutely pivotal effect on our understanding of AGN feedback in massive systems, so in particular galaxy clusters. And one thing just to point out here is that there's something special about getting to arc-second scales in these kind of systems, because that actually puts you at the mean free path scale in these kind of plasmas, and therefore the real physics of the system, the typical length scales over which you're going to get thermalization or other real the real microphysics will be accessible to you with arc-second scale imaging, and even going to a few arc seconds or 5 arc seconds is inadequate to access that level of physics. So with AXIS, our combination of soft X-ray response and our ability to see very low surface brightness because we're in low Earth orbit will let us basically push these studies down the mass scale, and we can start to see whether individual field galaxies have the same kind of processes going on. So this is a simulation of the CGM of an elliptical galaxy with AGN blown cavities in it, and you can imagine that, and this is a relatively short shortish observation, 200 kilosecond observation of this elliptical galaxy. You could imagine that the real physical processes that are going on are just as complex in these systems as going on in galaxy clusters. So I think this is an area where AXIS would break fresh ground because of its ability to study the low surface brightness emission in these sources in a spatially resolved way. Let me skip that and go to this one. Another area that the Decadal Survey put a lot of focus and weight on is time domain astronomy and time domain and multi-messenger astronomy. They sort of tend to go hand in hand to some degree. One of the digging down, one of the questions that they've addressed is what powers diversity of stellar explosions across the EM spectrum. So how do stars die? And this sort of folds into a lot of very important questions of production of heavy elements, the basic questions of how stars live and die, and also the physics of jets and what jets are made of. So by construction, AXIS will be able to actually execute rapid follow-up. By rapid, we mean about 2 hour response time. Follow-ups to triggers that we're getting from whatever is out there, whether it be a Rubin observatory, whatever ground-based gravitational wave detectors are operating at the time, LISA, IceCube 2, whatever's out there giving triggers, we can react to it. And if there's a localization already, of course that's easy, but we can also start tiling rapidly parts of the sky to try to detect. We will also plan to have onboard transient detection that will allow us to, if something goes off in our field of view while we're observing it, we'll be able to send an alert down to the ground. So for example, one of the things we expect to be able to see maybe hundreds of times during our mission will be supernova shock breakout that just happens to be occurring in our field of view when we're looking. So we'll have a transient detection running continuously on the data stream that will let us uncover that. And the sort of last, penultimate topic is is to look at the impacts that AXIS will have on exoplanets. The Decadal Survey has asked, how do habitable environments arise and evolve in the context of their planetary systems? And of course, to a large degree, this is in the remit of other wave bands to actually go and study exoplanets in great detail, look at their atmospheres, look at their chemistry. However, it's a little bit of thought. It's fairly clear that the activity of a host star, especially the high energy activity, the X-ray activity of a host star, has a profound effect on any exoplanets that are around it. They'll affect the chemistry of the exoplanets. In the extreme, of course, you can actually evaporate the atmosphere of the exoplanet if it's too close to a star. This is from Ukatao showing that the evaporation desert. Now, this is of course the thermal energy from the star, but it just goes to show that the star obviously is a very important determinant of the properties of the exoplanet atmosphere. Now, with AXIS, we'll be able to perform population level studies of stellar activity, flaring, coronal mass ejections, et cetera, and across the stellar lifetime, look at the effect that can have on exoplanet atmospheres. So you can imagine, taking the stellar activity that we'd be able to detail and starting to compare that with population studies of exoplanet chemistry that will come from other wave bands. And I think that will be tremendously exciting there. Now the final topic in this, again, dash through and coming to something which is near and dear to my heart, is the properties of dark matter. The Astro 2020 Decadal Survey asked an explicit question: what are the properties of dark matter in the dark sector? And one particular exciting area that's got a lot of the particle physicists excited and a lot of the cosmologists excited, is the idea that dark matter might be a very, very light boson, particular an axion-like particle, that are increasingly seem to be a natural prediction of string theory. So string theories are telling you that there's these that there should be these very, very light bosons around. So by very light, I mean, they could be as light as 10 to the minus 22 eV. And if they're sufficient, if they're that light, then in fact the dark matter will actually have a quantum nature on cosmological scales or on galactic scales. So this is a simulation showing how, rather than having nice your usual dark matter filament, you're actually getting quantum interference in your dark matter filament. So this is often called fuzzy dark matter. Now, it turns out that X-ray astronomy is a very powerful way of constraining the existence of these of this sector of physics. And one particularly powerful technique that I and my students and collaborators have been working on is using observations of AGN embedded in galaxy clusters to constrain this. So the idea is that you're looking at an AGN in the middle of a galaxy cluster. As the X-ray photons come out through the magnetized plasma of the galaxy cluster, then the physics of the axions, so the axion-like particles, tells you that some of those photons should be oscillating into axions as they propagate. And what that would do is distort the spectrum of the AGN that you see in your X-ray telescope. And these are sort of calculations of what those distortions should look like. So you think of these being multiplied into your spectrum. And the lack of distortions, if you don't see any distortions in your spectrum, you can use that to set limits on the physics of the axions, in particular the coupling constant of the axions to the electromagnetic field. And these are, this is the hunting ground that we use in this particular field. This is the mass of the axion-like particle, and this is its coupling constant to electromagnetic field. And you can see that these studies of cluster-embedded AGN, in particular Virgo here and HC 1275 here, have really helped us push down and rule out these large parts of parameter space. And in fact, the current strongest result is not quite on here. It's from my student Julius Cis-Renz, who looked at H1821, another cluster embedded AGN, and that pushes even a little bit further down than HC 1275. With AXIS, I'll show you Julia's more formal calculation of this in the next slide. With AXIS, we'll be able to push even further down here. And rule out even deeper into the parameter space. And Julia's shown that has gone through the simulations to show that with AXIS you can rule out axions almost starting to get competitive with what would be possible with Athena. And one thing to highlight is that in certain, the prediction of where you should be in this plane is not easy to make, even if axions are dark matter particles. But in certain dark matter models, these constraints, and if you were to propagate this up to 10 to the minus 12, which would still work, they start to clip the zones where you might expect dark matter to be. Okay, so that's a dash through the science of AXIS. In the last few minutes, let me just talk about how we make this happen. So as I said, we're a simple sort of single instrument design with X-ray optic and detector. Now the real key enabling technology that's finally allowing us to jump beyond Chandra is the X-ray mirror technology. This is the hard bit, the really hard bit. How do you build a arc-second quality mirror with 10 times the collecting area of Chandra? So the breakthrough here has been in Will Zhang's lab at NASA Goddard, and this is using the silicon mirror segments that are actually precision cut out of large blocks of monocrystalline silicon. So the semiconductor industry, you can now buy from the semiconductor industry, you can buy these large blocks of monocrystalline silicon, and then you just cut these foils out. And because they're cut from single crystals of silicon, there's no internal stresses, or very, very low internal stresses in these segments. So they hold their shape extremely well. You can then coat them. You can stack them together and align them into these mirror modules. So this is your double reflector, your hyperbolic parabolic double reflector. This makes a mirror module, and then you can basically tile those mirror modules around in some backplane that we lovingly call the spider, or the spider web. And this lets you build your area up. So in the axis mirror, this whole assembly is about 1.8 meters across, and we have something of the order of 15,000 of these individual segments that are making up our total mirror assembly. Just to sort of show you that this is not all just paperware. So this is probably, I believe, Will's hand holding up a real one of these polished mirror segments. And this is, some test data. And this is now actually a slightly old slide, but this is some test data showing that the individual segment is already as good as the Chandra mirrors. And then these are some test data at the module level. And again, this is now about 3 years old. This slide. But at the module level, showing that we can testing this, and back then Will was getting 2.8 arc seconds, but there's been good improvement since then. So that's how we're going to build our mirror. The detectors, baseline detector is the MIT Lincoln Labs CCDs. So these are the evolution of the detector that flew on Suzaku. And then Penn State will be providing our back-end electronics and our transient detection board. So the basics here are, we want to tile a 24 by 24 arc minute field of view sufficiently to oversample the PSF by a factor of 2. So we're going to have half arc second pixels, translates about 24 micron pixels. And then our baseline is to read this out at 5 frames per second, which basically gives us the same pile-up limit as Chandra, but like Chandra, we will have sub-array modes that will let us, if we have a single bright source we want to zoom in on, we'll be able to get significantly faster readouts in that source. And then this detector will be housed in what we call the X-ray camera module. So I'm not showing that here, but it'll be a housing around this whole thing, which will provide the vacuum door for the system. And then also we're planning a warm optical contamination blocking filter. We're trying to learn our lessons from Chandra and Suzaku, and do whatever we can to prevent the molecular contaminant from building up on the filters or on the detector. So we've been quite careful with our thermal design to try to do what we can to reduce contamination. So this is the team we have. So myself as PI, I say Richard is the former PI and now is chairing our senior advisory board, but basically and then Erin Kara is deputy PI of instruments. So the three of us are operating sort of as the PI team. And then the other thing I wanted to call out is we have by number, most of the people on the team are actually in these science working groups. We have these 5 science working groups that cover the full range of science, and in total we have about 150, or a little bit more than 150 people in the team. We're very proud that the science team is diverse. We have great gender diversity. We've got great ethnic diversity. Oops, sorry, apologies for that. And very much we're making sure that early career researchers are given key leadership roles, but with the mentorship as well that is only fair to provide if we try to have if we do that. And the before I move to conclusion, just to let you know the timeline of how this all goes. So the the starting gun was back in January, only back in January, with NASA releasing its community announcement. And then the draft AO is released this August. So the expected AO release is in July, next July, which means that the proposals will be due in October next year. So if you run down this timeline and all goes to plan, by late 2025, NASA should be down selecting the probe missions to the actual flight concept. And then launch will be 2032, and our prime mission will be 2032 to 2037. Okay, so let me just move to my conclusions and sort of just leave the two things that I want to sort of have you leave with. The first one is that Axis, we believe, will be a very powerful community facility in the 2030s, and I'm listing here some of the key characteristics of it. It'll also be tremendously synergistic to the other facilities that are up in the 2030s. The advantage of having a baseline launch date in the early 2030s is we now have a fairly good idea of what else will be there at that time. And so we're talking about the Roman, the Rubin Observatory, SKA, the ELTs. It's a little bit of uncertainty what will be happening in gravitational waves, but there's a good possibility that the Einstein telescope will be operating, or at the very least, we'll still have LIGO and Virgo operating. So Axis will be a very powerful complement to those. Okay, so I believe I've probably hit my time limit. So let me wrap up there, and I'm happy to take any questions.
Thank you very much, Dr. Reynolds. And I believe there will be a lot of questions. And let's start from the in-person attendees.
There's already a question in the chat.
Dan, do you want to open your mic and ask the question?
Yeah, I was just curious if the $1 billion cost cap includes 5 years of operations costs.
It has, yeah. The operations costs have to come under the PI managed budget. They have to come in under that 1 billion. The GEO costs don't. So anything associated with the GEO program, and including the actually running the GEO program, GEO funds, any software that would be needed specifically for the GEO program, that is handled separately by NASA. But the basic mission operations, yes, that has to sit within that 1 billion.
Okay, I got to say, great talk. I mean, I used to just clap at talks, but now with virtual, I see that people say that. So you.
Thanks.
So, any question from our in-person attendees? We have another question from online. Jay, do you want to open your mic?
I have one quick question. Would Axis be able to observe either sun or the moon?
Good question. The sun, no, absolutely, unfortunately. The moon, in principle, there's no reason we can't. Okay, let me be careful there. There's no safety issue for the satellite that we've yet aware of. Now, whether our optical blocking filters will be up to taking out the optical light and giving you actually a high quality X-ray signal from the moon is something we haven't looked at yet. but you know, if it's in principle, it shouldn't be a huge problem.
Yeah, thank you. I remember some of the telescope has a limitation on the star camera kind of pointing, especially when it comes to observing moon. So I hope you guys make it be able to, you know, observe the moon. So that would be a very interesting science there. So
yeah, agreed. Yeah.
Yeah, I hope you can hear me. So I know you spoke a bit about Athena, and I know that like part of the Athena mission has been like suspended, or like it's not sure if Europe has like funding for it. So I was curious, like with this access and like things, are people like taking it into account or like adapting the mission on that, or was that part of the decision making?
Yeah, that's a good question. So yeah, I mean, Athena's the Athena project has its challenges right now, and I mean, in short, the ESA has somewhat blindsided the project by telling them that there are, I think, 600 million euros over budget, with, and so that came as a big surprise, apparently. And so there's a redefinition process going on right now, or rescoping process, which might include simply shifting the costs away from ESA to another partner, to either a nation state or another country. You know, I wish them all the best for that process. It just don't know how it's going to go right now. Potentially Athena might come out of that process significantly doped. We hope not, but it might do. And then, you know, there's a separate process they've got to go through to decide whether whatever mission comes out of that redefinition process is still worthy of a flagship, you know, and still can be supported. Now, the consequence on Axis, I mean, there's a consequence for how we write our proposal in a formal sense, in that, you know, previously, formally, we had to demonstrate complementarity with Athena, and formally we now don't, because of all this. However, I think very naturally, a lot of the science I talked about with Axis will be complementary to Athena. It doesn't require Athena to be there, but if Athena was on the scene, especially Athena equipped with the XIFU, with the calorimeter spectrometer, I think that would be a tremendously powerful complement to Axis. So we certainly sort of recognize that. So it doesn't fundamentally change the way we think of Axis science. It changes a little bit of the way we phrase it, I think. Did that answer your question? Yes. Yeah.
Why does the collecting area change so much with energy?
Oh, that's a good question, and I guess I don't have the full effective area curve here, but let me just go to the slide though. Yeah, so you're referring to these two numbers. Yeah, so this is a very common issue with X-ray telescopes, that, you know, the to focus 6 keV photons, you need a much smaller graze angle than to focus 1 keV photons. So that means that the 6 keV, the high energy photons, tend to get focused just by the small area in the inner ring, because, you know, just geometrically that's the small graze angle. You have some control over this by setting your focal length. So our focal length, I don't think I mentioned this, our focal length is 9 meters, which is very similar to Chandra, which actually means we have a rather similar profile in how our area is dropping off. You know, our absolute area is higher, but the profile of how the area is dropping off is pretty similar to Chandra. If we were to appreciably shorten our focal length, so I don't know if you've heard of the StarX mission. The StarX is a mid-X concept that actually uses very similar mirror technology. It's an appreciably smaller mirror, but also because it's simply a mid-X, it's got a much shorter focal length. And because of that, the typical graze angles have to be much higher, and they lose the high energy effectivity. So yeah, so to some degree we can dial these two numbers by pulling our focal length out if we have a sufficiently big rocket to launch us.
Thank you. Alexei, I saw you raise your hand. Please go ahead.
Yep. Hey, Chris. Have you identified a threshold mission in terms of angular resolution? So if you have problems achieving 1 arcsecond, what's the threshold?
Yeah, I mean, I think our threshold, we're still debating exactly where that be, and you know, to a very large degree, we're letting the science working groups tell us what that has to be. So don't hold me to this, but the numbers seem to be coming out that 1.5 arcseconds on axis degrading to 2 arcseconds, or 2 point something small arcseconds at the edge of our field would be acceptable for a threshold, through a threshold mission. So that seems to be where the science is pushing us.
Thanks.
Yeah.
I saw a question from the chat. Can you subsample the PSF to 1/3 of a pixel? Yeah.
Good question. So yeah, so the issue is, just to, with Chandra, you basically can do that. The Chandra, you can do subpixel imaging, and you have some information of exactly where in your pixel the photon has hit from the charge splash. We're still assessing what we can do. In detail, it's a different CCD. There'll be a different distribution of charge deposited with the photons. So the straight up comparison with Chandra might not be straightforward. So we're still trying to figure out what we can do in terms of subpixel imaging with Chandra. For sufficiently bright sources, we believe we can centroid, however, to significantly better than a pixel, and in fact our science requirement for centroiding a source would be 0.2 arcseconds. That's where we feel we need to be able to enable the cross identification with other observatories. But that's of course for a whole source. It's not photon by photon.
Thank you. Margareta, do you want to open your mic? Sorry, I didn't recognize you.
Hi, can you hear me?
Hi there, how are you?
Hi, it's Margarita Karoska. I'm sorry, I'm coming on the number on Zoom. But thank you for the answer. I just wanted to comment a little bit further. Reaching the Nyquist, the 1/3 of pixel, has been tremendously important for Chandra, but also if we reach that, we could do the convolution and take out a lot of the PSF and sharpen it to 0.2 arcseconds or even more. So it is reaching the Nyquist criterion, which is 1/3 of a pixel, for not just the bright sources, but for many of the sources, will be really critical for a lot of the science that is being done.
Yeah.
So
I mean, one thing to highlight, of course, is with Chandra, the pixels are half arcsecond pixels, and the PSF is basically half arcsecond. We've got half arcsecond pixels and a 1 arcsecond PSF, so we're already oversampling our PSF by factor of 2. So that gets us in terms of centroiding. That helps a fair bit. But I completely. I mean, your point is taken. That and we are actually actively looking right now at what the subpixel capabilities would be.
Thank you.
For sufficiently bright source, we think the centroiding should be pretty straightforward. Realistically, the centroiding will probably be limited, and the thing we're really pressing on is just to make sure our astrometric knowledge is good enough to allow that centroiding.
Thank you. Anyway, I'm on a science team, but anything that I can help, because I have a lot of experience with this on Chandra, will be a pleasure. Thank you. Very nice talk.
I didn't see any raised hand and question from. Oh, wait, the last question.
Hi, Chris. Thanks. So, I wonder if you looked into how Axis how well it will be able to look at like the outskirts of clusters. So like, it would be complementary to like SZ, which can usually reach the larger radii, the X-ray, etc., to look at kind of either accretion onto clusters or yeah, kind of the ICM as it gets less dense further out.
Yeah, is that Jake?
Yes, it is.
Yeah, hi, Jake. Yes, we have. We have looked at that. I talked about the the science case for the CGM of ellipticals. The same capability, but more in the slightly harder X-ray, lets us see the low surface brightness ICM in the cluster outskirts. And indeed, these things are, as you know, often quite simulation dependent, but some simulations suggest we can push out all the way into the nearby filaments that are feeding into the cluster, that would actually would be sensitive to the diffuse emission out there too. So now with our field of view, we can do that quite effectively for slightly more distant clusters in one or very small number of fields of view. For nearby clusters, we'd have to start tiling, but we think that could be quite a exciting science area to look at cluster outskirts. Yes.
Very cool.
Let's thank Chris again. And see you next week.
Right, thank you.